In this video, you're going to learn about two very important theorems in calculus. The first is called the Extreme Value Theorem, and the second is called the Intermediate Value Theorem. Now we'll abbreviate these for short, EVT and IVT. Let's begin first with the Extreme Value Theorem, which states that if you have a continuous function f on a closed interval, and those are the two prerequisites, continuous on a closed interval, then the conclusion is that f must have an absolute maximum and an absolute minimum. Here are some examples for you. Notice that the pictures here are closed from A to B. The red dot on the left picture and on the center picture, they're showing you the absolute maximum values, where the yellow dots are showing you the absolute minimum values. So here's a maximum, and there's an absolute maximum. Notice that absolute extrema may occur at an endpoint. In the middle picture right here, it's the far left endpoint, that A value that is also the absolute maximum. And then the absolute minimum is marked by the yellow dot here and also here. In the case of the constant function, every single point is both max and min at the same time. So in this case, the absolute maximum and the minimum would be the exact same value. Now consider a function like y equals e to the x. This function right here on its domain of all real numbers does not have an absolute max or min. But as soon as I partition off this function, let's say from 0 to 3, well, now I do have an absolute max and min. That's what the extreme value does. It takes a continuous function on a closed interval and guarantees the existence of absolute extrema. But be careful, because if a function is not continuous, like in this example over here, this is a piecewise linear function. From A to B, I have a step or jump discontinuity, and there is no clear absolute max or min. These are open circles. So I have no value here on this left end and up here on that higher end. So I have no idea what those values are. We must have continuity across a closed interval in order for that to be true. More on that with derivatives as we progress throughout the course. But the next theorem, called the Intermediate Value Theorem, is one that's very useful and very helpful to us, as we'll see here in a little bit. And it, once again, has prerequisites. The first one says f has to be continuous. And the second one is that our element in question, which we're going to call y, has to be between f of a and f of b, the lower and upper bounds on the closed interval. And if those two prerequisites are true, then what we have is the existence of at least one number on the interval where the function at that number is equal to the element in question. So a lot of kind of symbolism here. I think a graph will make a little bit more sense, and then we'll also apply it to some situations moving forward. Before I get into the formal prerequisites and the guarantee, let me share with you some applications. And we discussed this in class earlier. Consider the temperature going from 70 degrees in the morning all the way up to 80 degrees at 12 o'clock noon. If that's the case, was there ever a time when the temperature hit 75 degrees? Well, that must have been true. I can guarantee that it was true. Temperature is continuous, and 75 falls between 70 and 80. Now, I don't know if it was closer to 12 o'clock noon or closer to 6 o'clock in the morning, but at some point on the interval from 6 to 12, we had to have passed 75 degrees. But as soon as I go to 81 degrees, now I'm no longer in between the two function outputs. And so the IVT doesn't necessarily guarantee my conclusion. It's possible that the temperature hit 81 degrees, but it's not guaranteed. So that's this idea about betweenness and continuity. Formally, jot this down. The two prerequisites for the Intermediate Value Theorem is, number one, f is continuous on the interval a to b. And then number two, the interval or the element in question, which I'm going to call y, must fall between f of a and f of b. And then the conclusion, the guarantee, says that there must be a number x equals c on the interval where the function value and the element will be equal. Let's kind of see how this works in an example. So here's an application. It says to use IVT to show that the polynomial function here, f of x, has a 0 on the interval 0 to 1. Well, let's begin by making sure that the prerequisites have been met. So I'm going to begin by writing number 1. F is continuous. Now, I can't just make that claim without knowing for sure that it's continuous. And remember that all polynomial functions are continuous. So polynomials are continuous. You wouldn't necessarily have to write that, but that's the reason we know f is continuous in this case. Now let's check betweenness. So my endpoints, or the lower and upper bounds, are going to be 0 and 1. Let's find out what f of 0 is. Let's find out what f of 1 is. F of 0 is -1, and f of 1 is +2. Now the element in question is this number right here, 0. Does the function have a 0 on that interval? Well, if you notice, the number 0 lies between f of 0 and f of 1. So betweenness checks out, continuity checks out, conclusion. I like to say ... or therefore by, and then please state the name of your theorem. By the Intermediate Value Theorem, you can abbreviate IVT. There exists a value x equals c on the open interval 0 to 1. I don't want to count the endpoints. It's going to be between 0 and 1, so don't include them. On the open interval 0 to 1, such that my f of c value is equal to the element in question. Now let's examine this a little bit more carefully here. On the backside, I have a couple other examples and situations here. Some of these are counter examples, but let's talk through them together. Does the conclusion hold true? Can IVT be applied to these situations? So here I have two function graphs. And on the vertical axis, I marked f of a and f of b. But look at where my element is, this little y value right here. In both pictures, notice that the y value is outside. There we go. It's outside of both f of a and f of b. So we don't have betweenness. IVT does not apply here. And I'll say the condition number 2 fails because y is not between f of a and f of b. Is the conclusion still true? Well, notice in picture number 1, it looks like there is some sort of value here, some c value, where f of c is equal to y. But that doesn't happen over here. So I would say maybe there's no guarantee. It may be true. No guarantee. Let's look down at example 2. Once again, does the intermediate value theorem apply here? Well, it looks like I have an element in question. Y does fall between my f of a and f of b ordered pairs. And same over here. However, notice that we don't have continuous or continuity in either case. So no, once again, IVT does not apply. Condition 1 fails. Condition 1, oops, fails. F oops. I'm trying to write, let's see here. F is not continuous. There we go, sorry about that. Is the conclusion still true? Well, once again, in picture 2, right here, it looks like I have an f of c value equal to the element y, but not over here in picture 1. So maybe it's true, but there is no guarantee. Stylus is struggling to write here. No guarantee. Okay. How about the third and final case? Let's see what happens here. Notice continuous function on a to b. Continuous function here on a to b. Yes, there's a little discontinuity moment happening right there, but it's outside of the interval a to b, so that's okay. We're only looking at the section here that is continuous. And notice that y falls between f of a and f of b. In both pictures, we're continuous. So IVT both applies, and the condition, or the conclusion, it does hold true. So in order to guarantee the conclusion that there is some existence of a c value on an interval, both prerequisites have to be met. Now I'll close this video with one final example, a numerical application. And it looks something like this. Here's a table of data, and it says Rochelle rode a stationary bicycle. The number of rotations per minute is given in this table from 0 to 9. Notice that the function here, r of t, is a differentiable function, and if a function is differentiable, it's also continuous. Differentiability implies continuity, which we'll talk about in a future video. Now the question says, is there a time t on 3 to 5, so that's kind of like my a and my b, my closed interval is 3 to 5, where the number of rotations per minute is 106. And that word justify means I've got to just say more than either yes or no. There is a time t. This is sounding like an IVT situation. I'm trying to prove the existence of a value on an interval. I'm trying to prove the existence of an intermediate value within the function. That's why we call it the IVT, or Intermediate Value Theorem. So, number 1, let's check for continuity. I'll say r of t is continuous because differentiability implies continuity. Condition 2, do we have betweenness? Do we have betweenness here? Let's check this out from 3 to 5. So r of 3, which is 95, and then I have my element in question of 106. That does in fact fall between 95 and 112. I'm looking right here in the table, just between 3 and 5. R of 5 is 112. So therefore, by the Intermediate Value Theorem, there exists a time on the interval 3 to 5 when r of t was 106 rotations per minute. Now, here are some strong and weak answers to that very same question. A weak response might be something like this one right here. They recognize the correct conclusion, but there's really not much of a justification. In this fourth example here, they're talking about 106 falling in the interval. It's a little bit vague. They have the theorem listed, which is good. Maybe our best answer right here, although it's short, is that guy. They have betweenness established. They have continuity established. It would have been nice to name IVT in that answer. And in the first one here, It says 106 occurs between 0 and 5, but we're looking between 3 and 5, so be careful that you look for the right endpoints. We have continuity and betweenness and IBT, so we can kind of see how these answers might be strong and weak as we move forward. That's how the intermediate value theorem works, and this is essentially how you might see it on a test question or on an AP exam free response question. I hope that video was helpful to you. Thank you for watching, and we'll see you in the next one.